So this talk I thought I'd give, it's just some work I've been doing fairly recently on the Ericksen-Leslie equations. Quite simple versions of the Ericksen-Leslie equations. You'll see they're one-dimensional in space and time-dependent, but still there's still stuff that kind of needs to be understood. So I'm going to show you some things, and then really at the end I'll just show the equation which comes out, and hopefully maybe other people can have a go at finding more information out about this equation with other techniques. Okay, so the motivation here, I'm going to have a one-dimensional system, so just one spatial dimension, but that's still important. I mean, lots of people are modeling and doing the theory of two-dimensional, three-dimensional space for liquid crystal applications. But actually, in fact, the vast majority of liquid crystal displays, which is the main use of liquid crystal in technology, are all one-dimensional systems. So the kind of market leader, as it were, well, kind of, is the, let me get this right, is the twisted pneumatic. That's what's in this laptop screen here, and in most TVs, although nowadays in-plane switching and vertically aligned pneumatic displays are well, there's a lot of those displays around as well. Okay, and all these things are in plane. All these things are one-dimensional in that through the cell, in this, what I'm going to call the Z direction, that's the only direction where there's variation in the director. And in different modes, this is a kind of twisting state in the in-plane switching, and here really the distortion only happens very close to the boundary. Okay, so here's a standard pneumatic cell. You might call it a Splay-Bend-Friedrich cell, where we have a really standard setup that was looked at a long, long time ago. And this is the kind of thing I'm going to look at here. So what we've got is, in terms of the geometry, we've got two substrates, normally glass slides or bits of plastic, basically, and often they've got electrodes deposited onto the inner surface of these two substrates. And they're flat, and I locate them at Z equals plus D and Z equals minus D. And in the middle, I've got a pneumatic liquid crystal. Okay, so in terms of independent variables, as I say, I've got one spatial dimension. I assume everything's homogeneous in every other spatial dimension, the transverse directions x and y, and everything depends on time as well. So the dependent variables are then, the ones I'm going to look at are the director angle, so this angle theta from the x-axis, the flow velocity, which is just an x direction velocity, v, and the electric potential, so I'm going to solve Maxwell's equations for this system, and I assume there's going to be a potential difference. So I'm going to assume the director stays in plane, in this x, z plane, although you can make headway when it comes out of plane as well, and because of the whole setup here, I only need to assume, well, I can assume it's because the director's in plane, that the velocity, the flow velocity is only in the x direction. Okay, so boundary conditions on theta, I'm going to show you a case where we have this pre-tilt condition. So there's a small, well, in general, in the cases I'm going to consider, this angle sigma plus and sigma minus are small angles. So I can prepare, or the experimentalists or the technologists can prepare the substrate such that the director is fixed at an angle sigma plus on one and sigma minus on the other substrate. In terms of the velocity, the flow velocity, I've got the standard no-slip conditions. And for the potential, the electric potential, I have a potential difference. So I'm going to think about switching this display as you would normally in a device. Okay, so Ericksen-Leslie, in general, Ericksen-Leslie can model lots of different situations, but in this 1D setting, I get two equations, effectively, for the Ericksen-Leslie part of my equations. There's one equation here for theta and one for v, my director angle and my flow velocity. So this can be thought of as the angular momentum. It's not quite got the dimensions of angular momentum, but it can be thought of as an angular momentum and a linear momentum balance. Okay, and in terms of the...
I'm sorry.
Yeah, sorry.
Is there word pressure? Is there a pressure? What happens to pressure?
Pressure. There is a pressure, but you can get rid of the pressure because you're only in one dimension, essentially. So what happens is there is a pressure, but because it's in this x direction, because you can't, the pressure turns out to be linear in x unless you assume that essentially the pressure is 0 or constant. So there is no pressure in that x direction, the pressure difference. Okay, so in terms of the director equation, we have fairly standard terms here. So director rotation here, so d theta by dt. I'm using these tilde because this is all dimensional still. I'm going to non-dimensionalize and get rid of all the tildes so that my equations eventually don't look messy. But at the moment I've got tildes because these are all dimensional quantities. So I've got director rotation, and there's this gamma 1, the standard rotational viscosity of a pneumatic. There's the classic elastic terms. Because I'm in plane, I don't get any K2 twist. I'm not allowing any twist. So I'll just get the bend, the splay in the bend terms, K1 and K3. I get an electric field coupling term here. So this is what's going to switch my liquid crystal from in different orientations. And so U here is the potential, and UZ is the electric field, effectively. And the director is coupled to the flow through this coupling term here. And then in terms of the linear momentum equation, I've got a flow inertia term. I've got what would classically be what would come out of Navier-Stokes, a kind of where the fluid viscosity comes in, where this G here is now an effective viscosity. The viscosity changes as theta changes, as the angle of my director changes. You can see that the effective viscosity here will change. And again, there's a coupling between the flow and the director through this term here. Okay. The final equation is for the electric potential, and that's Maxwell's equation. This is just the divergence of the displacement field if d is 0. There are no free charges here. And I can solve that. What we've got here is slightly different from an isotropic medium in that we have an effective permittivity. Again, the permittivity changes as my director angle changes. Okay. So then I'm going to non-dimensionalize. So I non-dimensionalize using fairly standard non-dimensionalization. Z now is there's only one length scale in the geometry, and that's the distance between the half distance between the two plates. So I non-dimensionalize Z by d, and I non-dimensionalize time here by the elastically driven director relaxation. So let's forget about flow for a minute. How would the director relax? It would relax on this time scale. Okay, so I'll use that as, I've got to pick some time scale to do this, to non-dimensionalize, so I'll pick this one. Okay, and there's various parameters in here. There's an elastic ratio constant, so the ratio of K1 to K3. So often many people will choose this ratio to be equal to 1, the one constant approximation, and essentially that's because you can see how that simplifies things. If K is 1, then I just get a theta ZZ term, and this term disappears. I have 2 timescales now, and this is important because I've got my first timescale that I talked about before. This is director rotation, simply because there's some elasticity in there. And the second one is a fluid inertia timescale. And it comes in, you can see here, it comes in as the prefactor outside the fluid inertia term, Vt. And in fact, what I'm going to do is take that as 0. Okay, so the difference in timescales between these two is at least 5 orders of magnitude. And so, except for very small times, where there's some reconfiguration of the velocity as theta changes, this then is not going to be an important term. If you want to look at the timescale of sub-microseconds, you might want to look at this timescale. But for anything, on the millisecond timescale, which devices often work, this then is not important. Okay, and finally there's some normalized permittivities here. They just come into, well, they come into, this means the factor here is 1 because we've divided by delta epsilon here, and it comes in as this normalized dielectric permittivity. Okay, so we can solve the electric potential equation quite simply. We just integrate twice, and we know some boundary conditions. The boundary conditions, remember, on U are that we have U equals 0 and U equals V on the two surfaces, plus and minus 1. And so we can solve the electric potential immediately. And you can see that an H here is this effective permittivity, 1 over the effective permittivity. And you can see here now that the electric potential is slave to the director configuration. the electric potential, because of what Maxwell's equations look like and the timescales we're looking at, immediately reacts to any change in the, well, any configuration of the director, and immediately has this form. Okay, and because it does that, it's essentially slave to theta. Okay, so we can solve that. That's one equation less. That's great. And we're left with this. So now we have these two equations to solve, and u, which pops in this switching kind of term here, u now is determined by this non-local term in theta. So I have to integrate this. This is a constant here, depending on theta still. This is a function of theta. But here, this is where the function of z is, but it depends on theta throughout the whole cell. And I've got some boundary conditions, so I look at my theta at my two boundaries as being these two angles, sigma plus and sigma minus, and the no-slip boundary condition. Okay, so how we're going to do this? Well, in fact, because now I've taken the fluid inertia to 0 on these time scales, I can then just integrate this equation as well. So I'll go through this. I mean, it's relatively simple, kind of turning the handle to get rid of this flow equation. But I'll just go through it just to, because it's important to know what assumptions you have to make along the way, in particular what boundary conditions you use. So I can integrate this equation by z. Okay, so that's just that integration there. I've integrated from some place in the middle of the cell, z, to, well, from -1 to that place. Now the key thing here is that this term is actually 0, because I've got Dirichlet conditions on my boundary, so d theta by dt is 0 at that. Theta never changes at that boundary. So I can set this to 0, and I can solve for the velocity gradient, but in terms of what the velocity gradient is at one of the boundaries. And here you can see it specifically depends on what theta is doing. But that term there, that's just I've just reproduced that term there. That term there can also be integrated between -1 and 1. And because I know my flow at the boundaries is 0, there's a no-slip condition. When I do integrate Vz, obviously that goes to 0. And so actually I can solve for Vz at this lower boundary. It's this, where this k here, this calligraphic k, is actually some functional of theta.
I'm slightly confused. Why isn't Vz equal to the line in the middle? Why isn't that equal to 0? Don't you have non-slip? Oh, sorry.
Vz.
Non-slip.
Yeah. So V is 0, but not the gradient, not the yeah. Yeah. Vz is dV by dz.
Yeah.
Okay, so we're here. So this k here is just a function of time. It's a constant at any particular time, but everything in here depends on time. So for any particular configuration of theta, this is a constant, but obviously theta is then varying in time. Okay, so we can now using this, we know the value of the gradient of the velocity at the surface. I can put it back into this equation here effectively, and I now have an equation for Vz throughout the cell, dV by dz throughout the cell, and it depends on theta. Okay, and so here we have the exact expression for I can integrate this, so here's the exact expression for the velocity throughout the cell at any time t. And k here is again just reproduced here, k is a function of time. Okay, so again, because we've got rid of fluid inertia, again the velocity, just like the electric field, is actually slave to this director motion. So as long as I know theta, and importantly, I'll come back to this, I need to know d theta by dt, then I can work out what my velocity, my fluid velocity in the whole of the cell. Okay. So now we've got a decoupled director equation. This now is what used to be m times Vz, the coupling between flow and the director rotation. So this now is my equation. Well, this is part of it. I've actually now got an extra term on this left-hand side. So this now is a completely closed system with some boundary conditions for the evolution of theta in time, with some non-local terms. The only problem is I've got this d theta by dt here. I don't really like it there, but I can do a bit more integration. I can integrate the whole of that. Well, I can slightly manipulate this to to find this term here once I've integrated between -1 and 1. And I can do that, and all that changes is, so this is the theta by dt I don't really like on this right-hand side. I can do that, and what I get is this. Nothing's changed except for this final coupling term here. And so what I get is this coupling term, which is a kind of an effective impact of the velocity, the flow, are these non-local terms. So they look rather horrible. So M and G are kind of like effective viscosities, and here's the elasticity coming in, and even the electric field coming into this non-local term.
So there's no initial condition for the velocity because it's given to you by the initial condition for theta.
Yeah, exactly that. Yeah. So that if that is not true in general, of course. Normally in a setup, you should be able to have an initial condition for theta and for v independent of each other. But the fact is that on that very small timescale of fluid inertia, that initial condition for v transforms into the condition given by the slave version with respect to theta. So on that microsecond timescale, v changes from whatever you want it to be, 0 or whatever, to what it is in this theory.
And if you set theta t is equal to 0, so looking at equilibrium, I'm just worried about that term on the right-hand side, which clearly should go as well, and I've forgotten the definitions of that go into it.
Sorry.
So if you set the left-hand side equal to 0 because we're at equilibrium, the term furthest on the right should equally vanish, shouldn't it? You don't want any effect of the flow on the equilibrium directed distribution. And unfortunately I didn't write down what the definition of that last term was.
That's just contained in these two terms here.
Right. Could you go back? Right. So you've got that. You've got that theta t, and you've substituted from the right hand side.
Well, if I integrate this, if I divide by this prefactor here, multiply by m over g, then integrate the whole of that equation between 0 and -1 and 1, I get an expression for exactly this integral here. And with that expression, I can put it back into k.
But that expression should include itself.
Yeah, the recursion.
Absolutely.
I'm trying to see how you avoid the recursion.
There's no recursion because this is just a constant with here. I'm integrating with respect to z, remember. This is only a function of t. So there's no recursion there. It's just there is a term that looks like this on the left-hand side and on the right-hand side. I have to put them together. And that's why I get the b. That's the division here. That's basically both those terms combined. Okay. So yeah, the theta by dt equal to 0. I think what happens is, so I've done this once before, what happens is, when that happens, both these first three terms here equal to 0, and therefore a equals 0.
Course, yes.
Yeah, so it happens that both of those things equal to 0. Okay, so where am I? Yes, okay, so the flow now is entered in two different ways. The rest of it's standard, the rest of it's kind of assuming there's no flow, you could have these terms here. But the flow now is coming by a rescaled rotational viscosity and a non-local forcing term. It's non-local because obviously there's an integral here, it depends on theta throughout the whole cell, and gradients of theta as well. Okay, so let's look at those terms separately. This rescale rotational viscosity, in fact, if I just look at that, the adaptation, the change because of flow, which is this second term in the circle there, then in dimensional form it's this, there's a minus here, m squared, gamma 1, g. All those terms, m squared is obviously positive, gamma 1 is always positive, and g is always positive because they're effective viscosities. You can get that looking at the dissipation. And so this whole term here is negative. And you can also show that the bracketed term 1 plus this is always positive. So it is an effective viscosity. It's never negative. You can call it a viscosity. And it's always less than 1. Okay, so what's this doing? This term is reducing the viscosity of rotation. So flow is always speeding up direct to rotation. In that term, at least. In the next term, this one here, this non-local forcing, well, we can't really tell, to be honest. There's quite a complicated expression here. it's very hard to understand exactly how that term is going to force the director rotation. We can do a little bit about this. Well, I'll just repeat this. In fact, all the terms on the denominator are positive. All the terms in the numerator can either be negative or positive. So I have no idea whether this is a positive or negative forcing term. It could act to increase or decrease the d theta by dt. Okay, but we can go a little bit further. Well, let's look at the boundary conditions. I'm going to just talk now about boundary conditions and experimental setups. So the boundary conditions I've set fairly general, in that theta at the two boundaries can be these arbitrary angles, sigma plus and sigma minus. The two standard setups that people use in the lab are either parallel rubbing or anti-parallel rubbing, and I'll explain those next. So for parallel rubbing, rubbing in general, what does that mean? So we normally get a substrate, and you physically rub that substrate. There's some kind of alignment layer, but you physically rub that substrate so that when you put a liquid crystal onto that substrate, it aligns in a certain direction, say in the x direction, but has a small pre-tilt. So this small pre-tilt could either be theta is sigma, slightly positive, or if I rubbed in the opposite direction, it will be negative. Okay, so these are two types of rubbing, forward and backwards as it were, and from those two types of rubbing I can make two different types of cell. I can make what's called a parallel rubbing cell, where I rub, once I've constructed my cell, the direction of rubbing was actually in the same direction. What this does, although it's called parallel, my directors now aren't parallel, unfortunately. The director at the bottom surface is sigma, and the director at the top surface is minus sigma. But I can put essentially the top surface on backwards, and then the rubbing effectively was in the opposite directions, and then I get the director at both surfaces parallel, both equal to this angle sigma. Okay, so those are the two different cases, and I'll go through both of those systems. So we'll start with this parallel rubbing case, where you can see there's what I'll show you is there is a solution which is anti-symmetric about the midplane, about z equals 0. The boundary conditions certainly suggest that, and there is indeed a solution like that. So here's my equations again. I've just reproduced these, nothing's changed. So now I've got these boundary conditions. I can actually find an odd solution in z. So theta is an odd function of z. And what does that mean in terms of a and b down here? Well, a here, you see this prefactor here is even in theta. Both m and g are both even, cos squareds and sine squareds. So that's even in theta. But all these other terms here are odd in theta. There's the theta zz, there's the sine theta, and again the sine theta that makes these all odd. Okay, so what does that mean? Well, I've got an odd solution in z. I'm integrating between z is minus 1 and 1, an odd function of theta. It means a just goes to 0. So for this particular case, when I've got this anti-symmetric solution, a is 0. And I'm left with this equation. The right-hand side now has no term which is to do with flow. It's effectively not seeing the flow except for in this rescaled viscosity. So for this system, when I have an anti-symmetric solution, the reduced rotational viscosity is the only effect of flow. So flow always acts to speed up switching, whatever I do. Okay, so that's fairly interesting anyway. If you want fast switching, then this is a geometry you might want to do, this parallel rubbing. For anti-parallel rubbing, well, there's not much we can do, except we do have some information from this kind of evolution equation for theta that we've created. There's two possible types of relaxation from an initial state. Sorry, let me just go back 1 second. There's actually, because my boundary conditions are theta is sigma on both sides, I can actually get a symmetric solution about the midpoint, and that is, as long as I don't do anything stupid, that's generally the solution I would get, a symmetric solution about the midpoint. But there are two ways. So let's say I've created some symmetric solution about that midpoint, and I want to see how it relaxes. Let's turn a voltage on and then turn a voltage off. We'll see what happens. Well, the first thing is what possibility is a simple decay back to an equilibrium state. So I've done a simulation here, just solving the 1D equation, and I start out with some distortion. So this is theta versus distance through my cell from minus 1 to 1. So there's a very small pre-tilt at both sides here, and And what I get, I've turned a voltage on, I've created a distortion where everything's kind of trying to align vertically with the field, so at pi over 2. I then turn the voltage off and it relaxes down quite nicely to zero, well, to the pre-tilt angle actually. That's one, just a simple decay. The other possibility is actually that I start out at this line here, so these crosses here. I start out here, and initially I do decay all the way back down, but it takes longer, and it takes longer because there's an initial increase in the director angle right in the middle of the cell. Okay, so it's rather unusual. This is called kickback. It's been known for a long time, and people who make devices don't really like it because it slows down the switching, well, the relaxation, the switch-off speed. Okay, so what can we, from our decoupled equation, what can we gather from about kickback? Well, just have a look at what that looks like as a function of time. So here's theta in the middle of the cell, so I'm just looking at this value of theta here. As time goes on, I start out at some value which is about pi over 2. It increases above pi over 2, so it turns even further than pi over 2, and then gradually decreases over, this is time in probably seconds actually. In fact, this is probably redimensionalized, yeah. And so if I look at then d theta by dt, that'll be just the gradient of this curve, I see that in initial times that gradient is positive. Okay, so for all this time here, the gradient is positive. My director angle is increasing with time. It's not what I want. I want it to go back down to 0. So what it does is it goes, it's positive initially, and then it's negative. And eventually d theta by dt will go to 0 at long time. Okay, so the equation I have tells me about d theta by dt. It's d theta by dt equals some big function of theta, or functional of theta. There's some integrals in there. So if I put in my initial state, theta at t equals 0, into this right-hand side and also into this effective viscosity, that will tell me what d theta by dt is just at that initial state. It'll tell me essentially that value there. Particularly what I want to know is that value at the middle of the cell, at z equals 0. Okay, so it gives me that first time step, if I think about it in a simulation way. But is that any use? What does that tell us? Well, it certainly would tell us whether we initially start to increase or decrease theta, whether we got kickback or not. So that seems interesting. So what I've got here is a virtual experiment where I've applied a voltage, I'm going to vary the voltage, I'm going to create a director distortion, and then I'm going to remove that voltage and look at how that initial director at the center of the cell responds. Does it increase or does it decrease? So all I've done now is exactly that. I've worked out at t equals t off, so that's when the voltage is turned off. I've worked out what my d theta by dt is at the midpoint of my cell at essentially time is 0 when I turn the field off. For different voltages. So for low voltages, we see that there's an initial decrease in theta. So that's really just the director, as I would expect, decaying back down to 0. But for high voltages, what I get is kickback. What I get here is that my initial d theta by dt, my initial d theta by dt is positive. So I go past pi over 2. And the previous simulations were for, I think, a voltage of 3, and I had about d theta by dt is 10. Okay, so there are two different regimes. One where I get a simple decay back to equilibrium, and one where I get this kickback. It's basically unwanted kickback. And also, the important thing here, actually, for if you're trying to optimize a device, is there's a fastest decrease of theta. This is where d theta by dt is in magnitude largest. In real terms, it's the most negative. So this seems to be the optimal point for to start switching your display, or the kind of voltage you might want to use. And this is simply from evaluating an integral, essentially, the right-hand side of my equation. I've not solved any differential equations here. I've just evaluated the right-hand side of my equation once. That's it. And in fact, it's quite nice because if I do the full simulation, if I solve for everything, theta, v, my electric potential, all in time, as I switch off the the voltage, so again, voltage is on this horizontal axis. What I've got here is a graph which is useful for people who do work out devices. It's the change in the optical retardation. So optical retardation is how a display works. It goes from white or black depending on the optical retardation. And what this is the time taken for this optical retardation to reduce by 60%. So it's a kind of switch from black to white, or white to black, depending on how you set it up. So what happens if I look at this graph? This is the full simulation. I again get a fastest switching time. This is a bit bigger. This is at above 1.5 volts, whereas previously I was below 1.5 volts. But I'm getting the same form. I'm getting the fact that actually I get the fastest switching, or decayed switch off, in this region of voltages. But this takes an awful lot longer. Well, not that long, I guess. It's just a one-dimensional system. But this takes microseconds on a computer to actually work out, whereas this might take. And the reason why this is important is in actual fact, you might want to vary a whole load of parameters. All the viscosities might want to vary, the cell dimensions. So you might want to do this run many, many thousands of times to actually really optimize your display. And so actually the speed up of just doing a single calculation will actually give you an awful lot of benefit. Okay, so what else can we do? We can also linearize. Now, so this kind of follows the original work of Frank Leslie, and I guess maybe someone else, I can't remember who, where they looked at a switch state and assumed the switch state was basically everything's at pi over 2. All the directors are aligned with the field. Let's do a perturbation about that. Let's look at how the modes relax and try and work out what happens with kickback. The problem is, so if you do that, you get many modes, obviously, and you think, oh, well, I'll just use the first mode, or the first two modes maybe, to see how the relaxation occurs. To get an accurate solution, you need thousands of modes to actually get a good approximation to kickback. So that's not so good. What else can we do? Well, we can do some things analytically. We can, if we do take a perturbation about pi over 2, so the switch state, then our equation, linearized, becomes this. Okay, so a nice simple, looks like the diffusion equation with a non-local forcing term. If alpha is 0, this is just the diffusion equation. Clearly, everything's just got to decay back down to 0 monotonically. But this is the interesting part. This is my non-local term effectively now linearized. Well, what can we do? So U is my perturbation away from my initial state. Well, it's actually possible to prove that as long as I've got a sufficiently large applied voltage and I turn it off, there will always be kickback. You can never get away from kickback. And so, well, how to do this? So we're looking at things, we're looking for an initial state which actually is in this set. So this is a set really simply that the U by the tau is greater than 0. Okay, so the initial du by d is actually positive, which is kickback. And you can work out a regular perturbation expansion for very large V of the solution to the equation to give you the initial state. So that's, we work out the initial state U at time 0. It turns out that for that initial state, the curvature, your dtu by dx squared, is actually exponentially small. So this term here is very small, but this term, this integral and non-local term, is negative and of order V, i.e. very large. And so you immediately see that this term here is always going to be positive, and you will always get kickback, a sufficiently large V. Okay, well, that's about it. That's where we've got. What else is possible? I don't know. So I just wanted to put this equation up, and maybe other people have got ideas. Maybe people want to investigate this partial differential equation with other methods. I have no idea what else to do, to be honest. But that's kind of what the program's about, just putting this up and seeing what other people want to do with it. Okay, but so I'm going to finish there. Thanks.
So I was trying to think what actually causes kickback, and it's deeply buried in these functionals that you haven't.
Well, no, it's not. It's not bad actually. You can explain it relatively easily.
It must be something to do with the fact that the director the second derivative of the director angle is high somewhere. That gives you a sort of flexing.
What happens is this. Well, it doesn't move. If we have an initial state, theta is a function of z, which let's say it's like this. Okay. Then let's decompose that into Fourier modes, whatever. The first two Fourier modes, the first two important ones, are that one obviously. But also, the next one is this, and it looks like that. It's that sign. So the director in the middle is a combination of this value here and this value here. The key thing is that this one decays faster as I turn the field off. So my director in the middle here is mode 1 plus mode 2, and this one's negative, and this one's positive, but this one goes to 0 faster. And so I effectively get an increase in that director in the middle of the cell. So if I draw on the actual initial state, which I've decomposed, it looks like that. So as these add up, this one and this one add up, I get this initial state. But this one disappears, and I'm left with that first mode. The first mode is slow. Okay, so when when flow is able to enhance this, it kind of slows down. When you have flow, it slows down the decay of this first mode. And that's why it hangs around more, and you get an increase in the middle of the cell.
Have you tried linearizing around small theta?
Yeah, you can do the...
Do the A and B go away?
Yes.
I'm sorry.
So, yeah, well, that's switch on. So that's...
No, when you switch off.
Oh, no, when you switch off, it goes, yeah. Yeah, A and B will go. And so, therefore, you get no flow effect. Well, I mean, you get the...
But you get the flow effect
on the other side, but you don't get kickback. Yeah, so, but that's what I guess it shows in... in one of these graphs. So this graph here, for a very small voltage, just above Friedrich's transition, here we're not seeing any kickback. But you can do that, yeah, absolutely. But it's not very interesting, to be honest.
It is for me.
Oh, it is? Okay, right, well, I've got that. Yeah, I've got that linearization as well, yeah.
We're looking at thermally excited modes.
Yeah.
And our experiments show that there is something funny going on with sort of effective viscosity
right.
for the lowest order mode, for this fundamental
that
mode.
one, yeah. Well, I mean, yeah, as you say, flow does affect it because of this term here. So that might give you...
Of course, this is standard.
Yeah.
That's for all
And this varies in space, of course, as well. It's not just a single effective viscosity.
Yeah.
It's different at the surfaces.
But if you decompose linearize in the
right.
mode, there you get very well-known expression for
Yeah.
the term on the left.
Yeah.
I was just wondering. I'll discuss
Well,
it later.
yeah, maybe not a linearization for small theta, but going to the next level, looking at weakly nonlinear or something like that might be useful. Okay. Yeah. I find you on that.
Very quick, is it a safe statement that weak anchoring could, in general, reduce kickback?
You kind of think physically that's probably true, but I have the equation. Well, the problem is, of course, I've used the Dirichlet conditions here to actually get this decoupling. Without the decoupling, I guess if you had a relatively simple anchoring energy, there might be some possibility of doing the same thing. I don't know, actually.
You can't think of weak anchoring as some perturbation of strong anchoring.
Yeah, it might.
The simplest.
It might be.
The simplest
Yeah.
cases,
Yeah.
with equilibrium.
Good.
Weak anchoring is if you rephrase it in the right way, weak anchoring is a perturbation of strong anchoring.
Yeah.
You have to rephrase it.
I guess so. I mean, I just think that possibly, your flow is 0 at the boundaries. So if your flow is 0 at the boundaries, then weak anchoring might not have too much of an effect. I don't know.
Right, can I ask another question? And that is that, surely it's always true that the lowest mode, even without coupling velocities, it's always true that the lowest mode is more slowly decaying than all other modes. So,
the
key here.
Okay. So if I do things badly and take my director equation and simply cut off, say velocity is 0. I'm not really allowed to do that, but many people do. You just say velocity is 0. I'll neglect velocity. Then no, you don't get kickback.
Because all modes decay.
Well, the modes decay. Of course, this mode does decay fastest. Well, not of course, but it's got the slowest. Sorry, this one's got more elasticity. That's what you would expect it to go faster. But I guess what's happening there, I've not done that, but I guess what's happening there is that this one isn't fast enough to get kickback. I mean, essentially this top mode here, because of the flow, is being held up almost. There's a flow there that's kind of keeping it there, whereas it doesn't affect this one as much. I think that's how I think about it. Yeah, John.
I was looking at the first two terms on the right-hand side of the top equation, which are interestingly not in divergence form, because, but nearly, because the derivative of k cos square theta plus sine square theta gives you twice the other term.
Yeah,
That means if you divide by the root of k cos square theta plus sine square theta, then that puts that term into divergence form. So that suggests you can make a nonlinear change of variables for theta, which would turn the first two terms into just a CZZ.
Okay. Yeah.
Well, I just wonder whether this was, because the other terms would then become, well, they would be functions of this, this new variable and its derivative or something, and you'd have a different prefactor to CVT. So probably that's going backwards in how you derive the equations, because I imagine they are in divergence form.
Oh yeah. So those first two terms, I guess, are just a variational derivative of that, the elastic energy.
Oh yeah.
That's what it is. The variational derivative of that is those two terms.
Okay, so that gives you the square root. That's right. So that's the square root of that z squared. Yeah. But it doesn't help.
It doesn't help, and I'm relatively happy with putting k equals 1, to be honest, as well. Because there shouldn't be a difference when you change k. I mean, there is a quantitative difference, but no qualitative difference should come out of that, really. No other questions? Oh, there is.
If you could go forward to your linearized model, can't you just integrate that once in x, and then you get the integral on the last line, or there if you want, and you get the variation of ux between the two boundaries, which would be uz in real life, I suppose.
I integrate that with x.
Well, you've got the second derivative of u with respect to x.
Yeah.
And then if you add ux at the two boundaries, I think that should tell something about Epiphanes' question, because if you take
Right.
weak boundary conditions,
That's what ux is given there, yeah.
then that would be 0.
Maybe, yeah.
And then you don't see anything. I don't know.
Yeah, maybe that's right, actually. And then, so you're doing the time derivative of the integral of u then? If you integrate this both, if I integrate the whole equation, you mean by x?
No, it is already the oscillation.
Oh, sorry.
Already the oscillation.
Yes,
of
okay.
Ux at the two boundaries.
Yeah. I don't know how, if I had weak anchoring, then yes, that you could apply it there, but in deriving this equation, I also assumed Dirichlet conditions in doing the decoupling. So we'll just have to work it out, work it all the way through to see how it worked out, yeah.
Okay. I think it is a general belief that if there is no surface viscosity, then weak anchoring usually works against kickback.
Okay.
But it is a belief, it's not a proof.
Right. Well, presumably people have just simulated it and solved the differential equations and looked at it there. But yeah, I mean the proof would be nice. Yeah, definitely.
With the weak anchoring, this boxiness of the initial condition goes away rather soon if you do calculations. So that means the second mode becomes much smaller.
That is actually, yeah, okay. So that statement, this thing here, it depends on doing a regular perturbation expansion for large V. The regular perturbation expansion with weak anchoring would actually be flat.
Either flat or
weak boundary layers, basically.
without the corners.
Yeah. And it's actually those boundary layers that make this term here of order V, because of that high elasticity in the boundaries. And if that goes away, then so it might be an interesting situation where for low V you don't get kickback, For high V, you don't get kickback either. There might be an intermediate region where you do get kickback. Right. That would be worth looking at, yeah. Okay. Okay. Thanks.